insurance an application to passport physics.
Okay, so our second speaker of this morning's session is Gbur, and he'll talk about deterministic vortex beams and other partially coherent singular beams.
Yes, thank you very much, and thank you to the organizers for the invitation to be here. I'm going to try and cram a couple of interesting things, or what I think are interesting, in a small amount of time, so hopefully I will do okay here. Part of what I want to talk about, of course, is just overall just the advantages of using some sort of structured light in free space optical communications. We know that light propagating in atmospheric turbulence suffers from distortions that can affect sensing and communications. Communications is what I'm always using as my kind of target objective to improve. We've seen over the years that partially coherent beams under the right circumstances can be resistant to turbulence, have some turbulence resistance. And on the flip side, we know that you can use vortex structures to encode and multiplex information, and that vortex structures are, in some sense, resistant to atmospheric distortions as well. And so what I've kind of been thinking about for way too many years now is, can we mix partially coherent and vortex properties together to improve communication systems? The problem, of course, is that a vortex is a deterministic phase structure, and when you're talking about a partially coherent beam, you're talking about a randomized phase. So the two don't necessarily mix together well. A lot of my work has been trying to see under what circumstances we can do something interesting. Now, just a refresher, but mainly to show a couple of pictures that'll be useful later. We know that, how do we use vortex beams for communication? Well, there are actually two ways you can think about it. We know that a vortex beam is a discrete topological phase twist, the topological charge. And for Laguerre-Gauss beams, we have an entire set of orthogonal modes. And this has actually led people to talk about, there's actually the two ways you can think about sending more data than usual using vortex modes. One is that the one that people mostly think about is you send binary data simultaneously through some sort of atmospheric channel using n different modes. So each mode, because you can separate them out at the detector, will be using will have its own independent data channel. The one limitation of that is, the big limitation of that is mode crosstalk increases rapidly. So your independent modes become not so independent in a very short propagation distance. A more robust thing is something that people don't talk about as much, but it's kind of where I started, is you could send n-ary data through effectively an alphabet of n different topological states. So instead of n independent beams, you have one beam, but the vortex order indicates sort of a letter of the alphabet you're trying to convey. So you're conveying more information through that. Limitation there is you actually have to measure the actual vortex structure, which is going to require phase measurements, interferometry, or things like that. Now, just a quick coherence basics, so I think everybody pretty much knows most of this already. We'll be working with a cross-spectral density, which we can think of as the ensemble average of a monochromatic field at 2 points in space at a single frequency. We know that for quasi-monochromatic fields, we can just think of that, we can just use a cross-spectral density to single frequency. And we also know that we can write the cross-spectral density in terms of sort of the fields at the 2 points and the correlation function between them. And this brings me to the deterministic vortex beams, which is sort of the first topic I want to touch on today. And just to give you a little history, because I think this is sort of instructive in the way that research often works, is since 2004, I've been using something that I call the beam wander model to construct partially coherent vortex beams. I often kind of tease Taco that he does Young's double slit experiment for everything, and this is essentially my Young's double slit experiment. I've been using it for everything for 20 years, and because it just keeps being useful for me. And the original idea was that back in 2004, we were starting to look at partial coherence and vortices, and I wanted a way to impose that I have a partially coherent field that definitely has a vortex in it. So if you use a vortex field here, then you're just displacing the center axis of your vortex beam, and your integral over R naught is your ensemble average that gives you your random field. So no matter what the cross-spectral density looks like in the end, you know you've got a vortex. Well, in 2020 with some colleagues, we were looking at extending sort of this family of beam-wander beams, and Joensuu Zhang came to me and said, well, I started propagating these things, and it looks like they're becoming more coherent. This is the phase structure, the cross-spectral density. It looks like they're becoming more coherent and more deterministic as they propagate. And this pretty much nearly gave me a heart attack, because as I said, I've been using these things for 20 years, and suddenly it seemed like there was something very wrong with this model. Because you don't expect, when you randomize a field, you typically expect things get less coherent, less deterministic as you propagate, and here we are seeing kind of the opposite. Well, fortunately, the answer to this was buried in one of my own papers from years earlier. And that is that these beam-wander beams, which I've since started calling Rankine vortex beams instead, Grover Swartzlander and colleagues, and I think about 2007, were looking at partially coherent beams, noted they had, in a sense, a Rankine vortex structure. But most people, when they think of doing partially coherent vortex beams, they might think about doing a shell model case. You start with a vortex and you randomize it. And that mu naught for shell model, you can break up into a spectrum of plane waves. So you basically are treating your field as an ensemble of tilted vortex beams. But a bunch of tilted vortex beams, if you pass them through a lens, a bunch of tilts become a bunch of shifts. And that means that you've got your beam wander or Rankine beam. So basically you have a Fourier relation between the basic shell model case and the Rankine case that I was looking at. And so this reassured me, because when you propagate to the far zone, you're also taking a Fourier transform, which means that when you go to the far zone in the beam wander case, you get the shell model case, which means that that vortex built into your system sort of reappears. But this got me thinking that, hey, we could use fractional Fourier transforms, and we could stick that seemingly deterministic vortex structure any propagation distance we want, because a fractional Fourier transform works like basically similar to the Fresnel propagator. And so, whoops, I won't go through, let's see if I can go the right direction. Won't go through all of it, but you have basically the idea is we start with a shell model case, we break it into a series of tilts, we fractional Fourier transform every member of the ensemble to get a modified source field. And then for mathematical purposes, it's very nice to say, well, let's just free space propagate each of those source fields first, and then we can do the final integral, the ensemble average at the end, to find out the cross-spectral density. So we can find the cross-spectral density at the source and at any propagation distance. And you find that, whoops, I really need to figure out how buttons work these days. You find out that there's a special z distance at which the Gaussian shell model beam will give you a pure vortex state. And it depends on alpha, which is a fractional Fourier parameter, k, free space wave number, and sigma is just the beam width. Interestingly, spatial coherence doesn't come into this at all. And so my student was simulating this, and sure enough, when you propagate a partially coherent field, this is again the phase structure. We're fixing one observation point in the cross-spectral density and looking at the phase with respect to the other. The special distance is 100 meters. At 100 meters, you get a perfect vortex. If you're away from 100 meters, in front of or behind, you get what you normally see in a partially coherent vortex beam. You get equal and opposite vortex pairs. And that's the intensity cross-section. So it actually works that you get this sort of pure vortex, or nearly pure vortex, at a special propagation distance. And this can be done at pretty much any propagation distance you want. This is at 1,000 meters. And also, you can also define what you might call a depth of field for this pure vortex mode. You can say, how long can it propagate before it stops really looking like a pure vortex, and you get, for instance, those two vortex pairs in place. And that depth of field, as I call it, the one interesting thing is, as I said, the position at which you can place this deterministic vortex doesn't depend at all on the coherence, but this depth of field that you get does depend on the coherence. So if you make it a very incoherent field, you still get that perfect vortex at a certain distance, but now we're talking about a few centimeters before the field doesn't look like a perfect vortex again. And part of what we're doing now is starting to look at propagating these in atmospheric turbulence, because that was kind of the whole point, is to say, what happens, does this beam act more robust, and can we get this vortex out after propagating in turbulence? And this approach is sort of that Enery sort of approach for encoding. We want to just be able to encode a single vortex state of any order at a particular distance. As a complement to that, I'd like to mention another approach we've been doing and got published recently. I've talked for a number of years that you can kind of break down partially coherent vortex beams into three classes. One are these Rankine or beam wander vortex beams. There's also the classic twisted Gaussian shell model beams, which have a twist in the correlation function, in essence. And these circular coherence beams, also called separable phase beams, that we started looking at. Incidentally, when Professor Hyde mentioned there have been work showing the robustness of partially coherent vortex beams in turbulence, I freaked out because I didn't realize he was talking about my work. I was like, oh, so who did this? And I didn't know. So circular coherence, just briefly, the idea Professor Hyde already mentioned, you have sort of a kernel with and you have a cross-spectral density that's made of like a kernel and a probability function. You use a non-negative kernel. Here we're using that focusing kernel again. And that kernel doesn't depend, the field in that kernel doesn't depend at all on the parameter that you're varying. So in the end, your cross-spectral density is going to come out with a pure sort of deterministic field structure and some randomness only in the radial dependence. And that's exactly what you want for a partially coherent vortex beam. You've got a deterministic phase, azimuthal phase, randomness in the radial direction, and the question is, does that help you again? And incidentally, especially since Sergey is here, I wanted to give a shout out to his early paper on partially coherent beams with a separable phase, which is really the first paper that I know of that really said, hey, we can make a partially coherent field with this deterministic phase structure. Now, with one of my students, we started looking at the OAM spectra of these three classes in turbulence and trying to get a big picture feeling of, is one class of partially coherent vortex beam better than the other? And for instance, with the Rankine vortex beam, this was not surprising. So here's the spectrum basically in free space in blue and turbulence in red. And as you decrease the spatial coherence, the sigma g, well, you start to see, well, yeah, in turbulence it starts to look less affected and looks more similar to the free space case, but it comes at the cost of course, the free space case is pretty terrible OAM spectrum to begin with. And what I was really curious about is, are there situations where, nevertheless, the partially coherent case does better? And interesting thing is, it turns out, yeah, actually kind of frustratingly, like many things in atmospheric turbulence, like propagating in turbulence, the answer is the optimal beam apparently depends on what sort of system you're looking at, as always. So you have to decide on your system first, and then you can get your answer. So in this case, we took those plots I just showed you of the OAM spectra, really hard to get an estimate of what's good or not from that. So we looked at the standard deviation of that OAM spectrum, and you've got a coherent beam. Then your circularly coherent beams start off much better than any other case, but at some propagation distance, they end up being worse than the Rankine beams or the twisted beams, which end up being much more robust. So it really does depend on how far you're propagating, what your turbulence strength is, and so forth. Incidentally, another amusing lesson to me the first plot of this my student brought me covered about that range. And he showed it to me and said, well, it looks like you were right. It looks like the circular coherence does best. I said, but it looks like one might intersect the other if we go out further. And sure enough, that's what happens, is that after a certain propagation distance, the Rankine and the twisted beams catch up and you get a better OAM mode spectrum than the circular case. So, wrapping up, I can just say there are a couple of different ways you can encode information in optical vortex beams, and we're kind of, the two topics I mentioned here are covering the two bases. You can look at deterministic vortex beams, where we're just trying to get as pure of a vortex state as we can at a detector to encode by sort of an alphabet of vortex states. And for the modal approach, where you really want to encode information on independent vortex beams, different partially coherent vortex beams may be optimal depending on circumstances. And those are my students who worked on these projects and the papers that came out of it. Thank you very much.
Okay, thank you. We have time for some questions. Please do not ask why his students look so miserable.
I think they're calling for help.
So, thanks for the interesting talk. And in this case where you were comparing these two or these different kinds of partially coherent models together, I was thinking that because of the circular coherent case, you can kind of adjust where it focuses with the choice of coherence width.
Yeah.
So if you choose the coherence width differently, would it actually be better than the Rankine in different cases? Or
Yeah, that almost certainly we can probably play with the parameters, especially with circular coherence,
yes.
to improve one way or another. So this is sort of the preliminary results, which allowed my student to graduate. And next we have to push kind of more fully into the parameter space and say, how much do each of these parameters
Follow up on that quick one. So in the circular coherent case, you can play with the parameters. Is there something like that in the Rankine vortex?
Well, yeah, you've still got you've got sort of effectively the spatial coherence, which is kind of equivalent to the beam wander, inversely related to the beam wander. In addition, you've got the overall width of the beam. Those are the main two parameters, other than the vortex order. And I imagine there are other possibilities of tweaking it, but that's sort of keeping it as simple as possible. For these three fundamental classes, you can definitely make beams that have even more complicated OAM structure we have. I focus on these three as sort of a nice fundamental distinction. Rankine, the twisted beam acts a lot like a rigid body rotator in mechanics. The separable phase acts very much like a fluid body rotator, and the Rankine acts like something in between the two. So they were a nice starting point. Thank you.
Any other questions? Yes, go ahead.
I'm not sure if you consider only vortices with the topological charge 1 or also with higher topological charge?
Yeah, in this, actually, so for this plot, it was only one, and for the twisted case, it was basically choosing the twist to be comparable to a vortex of order 1. But also, we want to go to higher order. Again, the interesting thing is my student Arash did all these calculations analytically. Basically used a simplified turbulence model, a lot of Gaussian integrals. And so he fought his way through all of these analytic calculations just for order 1. We'll probably go to some computational methods to do higher order. And you'll definitely see some variations.
I'm worried about the vortex splitting and...
Yeah, and that's where you run into interesting challenges with, the vortices will split, the modes will overlap more, you start to lose vortices at the boundaries and so forth.
Okay, I think in the interest of time, we should stop here and thank our speaker once again.